and there was a truth table for the if-then statement, and the rule was the only time an if-then statement is false is if the first part is true and the second part is false. And we base that on whether the person who said the statement it was lying or not. You know, the original conditional statement. So we're going to talk about the conditional, but there are three other statements which you probably have had already in geometry, because I went to the SOL page and checked to see what you guys should know about this. So you've heard this before. I don't know if you've actually seen it relative to truth tables. You may have just been told this is what they are, but I couldn't find any discussion of truth tables and these other versions of the conditional statement. So if you remember, the conditional is the if-then statement, and we show it by this symbolic logic: if P, then Q. So the other statements are taking the conditional statement and making some of them negations and maybe switching the P and the Q. So there are three possibilities, and we'll look at each one of them, and we'll use an example to demonstrate what they are. And the question is, are these statements equivalent relative to truth tables, or are they not equivalent? So the other three statements are the converse, the inverse, and the contrapositive. So if you take the original conditional statement with statement P and Q, and you just switch the P and the Q, so instead of if P then Q, you have if Q then P. That's called the converse. And it turns out that we'll find out later that if the conditional is true, then the converse may be true, but is not always true. Now the next one is the inverse, and we don't switch the order, but we make them both negations. So it will be, instead of if P then Q, it's going to be if not P then not Q. And again, if the conditional is a true statement, sometimes the inverse is a true statement, but not always. And the final additional variety of this is you change the statements to the negation and you switch the order, and that's called the contrapositive. So if not Q, then not P. Now you may have heard in the past that these two are the same. If this is true, then this is true. If the conditional is true, then the contrapositive is true. Always. But we're going to show why that is the case. And it's in your book, so I'm going to show you a truth table for the conditional, which we already know. The truth table for the conditional is it's only false if the first is true and the second is false. We'll look at the truth tables for the others, the results. We'll do one of them, but we'll just show you the results, and we'll see that from a truth table standpoint, the conditional is not equivalent to the converse, and also not equivalent to the inverse, but it is equivalent to the contrapositive. Okay, so we'll skip that. We've already said that. So here's the table that's out of the book. So here's our possible values of truths and falses, like we normally have a truth table. Here's the truth results for a conditional statement. It's only false if the first one is true and the second one is false. Now these are the results of doing the truth table for these other if-then statements, where we switch P and Q, we make them negations, and we switch them and make them negations. So this is the symbolic logic associated with the three other situations. So let's actually do one of them just to show you how you come up with these results. This one is just the truth table for the conditional. So we're going to do the last one. So we're going to need, to make the truth table, we're going to need P and Q. we're going to need a space for the negation of Q, a space for this, and a space for the negation of P. So we're going to need five columns and 5 rows. And we're going to show you how we got the number in the table. And then you'll just have to take my word for it that the other two are correct. Okay, so we have P and Q, and then we have the logic statement for the contrapositive, which is if not Q, then not P. So again, for a conditional statement that involves, well, just any logic statement that just involves 2 statements, P and Q, simple statements, the 4 possible combinations are these. And we use that pattern, 2 trues, 2 falses, alternate the trues and falses. Okay. The next thing we do in truth tables is we take whatever we have here and either copy it or copy the negation. So because we have the negation of Q, we're going to not copy this, but we're going to take it and switch the truth values. So this true becomes false, false becomes true. Likewise over here, we take the column with the P truth values and we change them to falses when they're trues, and we change them to trues when they're falses. And then we compare the truth values in these 2 columns for a particular row using the rules for the conditional statement. So which one of these rows, let's call this row 1, row 2, row 3, and row 4. So Janai, which one of these, there's going to be one of these 4 rows which is going to be false. This one here? So what's the rules for the conditional? If the first one's true and the second one's false, it's false. So which row has the first one being true and the second one being false? Second one, right? So this is false, this is true, this is true, this is true. And if we compare that with the conditional statement, well, you can see that's how they got this answer. Okay, so what they did is they did the truth tables for these 3 things. They got the result and they just put them in one table. So you can see true, false, true, 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 false, true, true. That's where that comes from. So we could do the same thing. The key thing here is that if we compare the final values here, that for the conditional and the contrapositive, they have the same truth values for the same input. The output is the same for the same input, you get the same output. But if you look at the converse and the inverse, in this case, you get a false here, you get a true there. Here you get a true, you get a false there. So they're switched. The middle ones are switched. And so these 2, this is not equivalent to this one because they're different. These 2 are equivalent because they're the same. And these 2 are equivalent because they're the same. So that's how we tell whether statements are equivalent, by comparing the last column in the truth table. Okay, so that's how you prove they're equivalent. Let's look at an example. So let's go here. Actually, I was going to use, that's the second example, but let's do the first example. The first example is the one that I used the other day. If you study hard, then you will get an A. Okay, so that's the original conditional statement. It's an if-then statement. The converse, this is if P then Q. So the converse is if Q then P. So all we do is we identify this part as P and this part as Q and just switch them. So then you'd have if you get an A, I'm slightly rewording them. If you get an A, then you have studied hard. Okay, so that's the converse. The inverse is you keep the same order, but you change them to negations. So go back to the original condition and make those negations. So if you don't study hard, then you will not get an A. And then the final one is the contrapositive. And there you're switching them and making them negations. So again, you can go back to your original conditional statement. So this is the P part. This is the Q part. So we're going to do the Q part first. So if you do not study hard, then you will, no, that's the wrong way around. I got to switch it here. Let's go back. Sorry. I was starting to read that. I said, that doesn't make sense. Okay. If you do not get an A, then you didn't study hard. So we didn't say that the converse is not, if the conditional is true, you studied hard, and the conditional, the requirement, the if versus then, if that's true, sometimes that is not necessarily true if you look at the converse. If you get an A, then you have studied hard. That might be true. You may have gotten an A and you studied hard, but there may be people who didn't got an A but who didn't study hard, and that doesn't contradict the original conditional statement. Likewise, if you don't study hard, then you will not get an A. Again, the original statement says if you study hard, you will get an A, but it doesn't mean that if you don't study hard, you can't get an A. The last one is if you do not get an A, then you didn't study hard. So that one is, if the original one is a true statement, then that one is also a true statement. So here's another one. Somebody asked, where did you come up with that, this saying? So the first thing we have to do actually to write the other three different situations is we have to make this into an if-then statement. So if you are a bird, and I'm going to take the flock together part because that's irrelevant. Well, it is the flock feather. The feather part is sort of irrelevant, and it just make it easier to think about. Okay, if you are a bird, then you will flock. I guess what I will do is I'll say you will form a flock. I'm trying to do it in a better form of in English and still be consistent or correct. Form flocks. Okay, so if you're a bird, birds flock. So this is a true statement. If you're a bird, and birds, when they group together, they become a flock. Okay. So the P statement is you are a bird. The Q statement is you will form flocks or a flock. Let's put a flock instead. If you're a bird, you will form a flock with other birds. Okay, so that's the original conditional statement that I have taken the original statement, which wasn't conditional, and I made it into, well, it wasn't an if-then statement. So I created it into an if-then statement. So let's see if you guys can, so I'm going to give you some time here to write down what you think the other ones are, and I'll write out because you'd be able to use your cheat sheet. So here's your cheat sheet. So you'd write down that the converse is if Q then P. The inverse is if not P then not Q. And the contrapositive is if not Q then not P. Okay, so go ahead and write the three other ones. All you have to do is understand the symbolic logic. So in the case of if Q then P, you're going to switch the Q statement with the P statement. And the other ones you're going to have to create the negations, which pretty much means putting not in this case. And then I'll ask somebody what they got. In I'll give you a couple minutes to do that. Or at least if you're not going to write it on your paper, think about what you're going to answer if I ask you the question. Okay. By the way, this birds of a feather flock together, we looked it up yesterday in class, and it's some 16th century saying, and it's using Old English, so it's kind of an interest. It's if ye of a bird, it's something along those lines. I ought to find it again just because it's kind of interesting. So while you're working on that, I'm going to find this saying. So how many people have heard that saying before? Birds of a feather flock together. Yeah, somewhere. Some point, yeah. We can find it in Hindi. That'd be interesting. So the meaning is those of similar taste congregate in groups. This proverb has been used since the mid-16th century. In 1545, William Turner used a version of it in his papist satire, The Rescuing of Romish Fox. Birds of one kind and color flock and fly always together. First known citation in print is from some dictionary. Birds of a feather will flock together. Men of my age flock together. We are birds of a feather, as the old proverb says. So there you go. So let me pick somebody. Zach. So what is the sentence for the converse?
It would be if you form a flock, then you are a bird.
Okay, good. Okay, let's see. Jenna Klein, what's the inverse? Yeah, if you are not a bird, and let's see here. Robert Faulkner. So what's the contrapositive? So if you don't form a flock then you are not a bird. Okay, so the question is, so I've got to search on Google because I don't. Somebody mentioned this yesterday, so I was going to. So a flock, as a where is it here? Flock, people, science, other. There we go. So it's a behavior exhibited by when a group of birds called a flock. Okay. The question is, are there other things that can be flock come together? And I just saw something that said yes, it could. So let me go back one here. It seemed like the first definition. Here we go. Flock, a group of birds. Flock, a herd of sheep, goats, or similar animals. So it turns out that birds, I always think when you think of something flocking together, you think of birds. But the reality is that a herd of sheep, goats, or similar animals can also be called a flock. I guess that's in the Bible, right? A flock of sheep or something like that. Okay. So that's if the only thing that was a flock was a bird, then all of them would be true. All of these statements. But in this case, because there are other animals that are not that form in flocks, they're not birds, then if you look at the contrapositive, if you form a flock, then you are a bird. Well, sheep can form flocks, and they're not birds. So that's an example where the converse is not true based on the original one. If you are a sheep, then you will form a flock. So there's, in this case, it is true, but not all of these involving flocks. The same way here, if you are not a bird, then you do not form a flock. Well, again, a sheep is something who's not a bird, and they do form flocks. So that's contradiction to that one. Whereas here, if you don't form a flock, then you are not a bird. So, if you are like a school of fish, you're not a bird. Okay, that's true. So anyway, that's kind of the way you go about this. Just be able to take an if-then statement or something that can be converted into an if-then statement and be able to write the converse, the inverse, and the contrapositive. And what we've done here is, we've shown that these are equivalent by using truth tables. So if I give you an example, I could give you one of these and ask you to create a truth table to show that they are equivalent. Now there's also, in this question of taking sentences that are not necessarily if-then statements explicitly, but can be converted into if-then statements, the book gives you a listing of other possibilities. These are not all the possibilities because birds of a feather flock together doesn't fit any of these. So these are just other examples. So here's the normal one that we like to use. But also if P, comma Q. Sometimes the then is implied. So if you are a bird of a feather, you flock together. So I left the then out. Okay. If you are a bird of a feather implies that you are a flock of a feather. That is not quite as poetic as the other one, but it's still okay. You are a bird only if you flock together. Being a bird is sufficient for you to flock together. I'm not going to ask you to memorize these things. It's just to show you that there are other translations. Okay, moving on. The last statement, which has a truth table, is called a biconditional. And instead of saying if P then Q, what you say is P if and only if Q. And instead of having a single arrow, you have a double arrow. And what they say in the book is that this is equivalent to that. So P if and only if Q is the same as if Q then P and if P then Q. So it's kind of like the contrapositive. Well, it's not exactly like the contrapositive. It's actually the converse and the inverse. This is the case where they're both true. And a lot of times this is used in math proofs. I'm going to give you an example. I'm going to give you two examples. So if you do the truth table for this definition of the biconditional, so we have two columns for P and Q, all the four different options. Then what we can do is we can do if P then Q here. I just copied that from the converse. Okay, so this is the converse. If you go back to that table that's in the book, you'll see it's true, true, false, true. This is just the conditional, the normal conditional rules. It's only false if the first is true and the second is false. And then we apply an and statement to these two. So the only time an and is true is if they're both true. So these are both true, so the result is true. These are both true, so the result is true. And in this case, they're not both true, so they're not true. So that's how you derive the truth table for the biconditional. And here it is. So it's like the conditional, except it's false also when you have false then true. For the conditional, if you have false and true, you have true. So the way that we derived the conditional table was we said, is the person lying? Here's the statement. Here's the result. Did the person lie based on if he told the if the P part was true and the Q part was true, the result was true. What if I make the P false and Q true, or P true and Q false? Is the guy lying? So what is the idea behind the biconditional? Well, the biconditional is pretty much it's saying that if this happens, then the then only happens under those conditions. It's very restrictive as far as, so you won't, not only do you not make, don't you lie, but you don't make anybody mad. Okay, we're talking about mad, So when we did the thing about, well, we'll use that as an example. So this is not asking the question. Pardon me? No, not really. It's kind of like when we talked about the conditional. And we use the example, if you work hard, you'll get an A. If you work hard and you get an A, then you're happy because that's what I said you do. If you didn't work hard and you didn't get an A, then you're not mad because that's what I said I was going to do. The one that kind of is wishy-washy is you don't study hard and you still get an A. The people who studied hard are not going to be happy about that. I didn't lie, but they're not going to be happy about that because they thought that was the only way that you were going to get an A. I didn't say that. What I said was if you study hard, you will get an A, but I didn't say that if you didn't study hard, you wouldn't get an A. Okay. I just guaranteed one thing. Whereas the biconditional is there's nobody that's upset when I say that. Okay, you'll see why in a second. But I'm going to use first, here it is. Okay, so the biconditional form of the example is you will get an A if and only if you study hard, versus if you study hard, then you will get an A. It seems like it's the same thing, but as we've seen, there is the case of somebody not studying hard and still getting an A, and then the people who studied hard are like, I didn't, maybe I didn't need to study hard. I could have still got an A. Whereas here, the only way to get an A is to study hard. So if you look at the truth table, we basically have the first and last conditions where, so the first condition is I study hard, I get an A. Okay. That's what he said. I didn't study hard, I didn't get an A. That agrees with what he said too. The other two conditions, I study hard, I don't get an A, that is, you don't want that to happen. Or somebody, that's if that happens, not only did I lie, but you're not happy. Okay. The second case is I don't study hard, or I don't study hard and I get an A. I'm not lying, but I'm mad. So in this case, if I say you'll get an A if and only if you study, then it's much more restrictive, and everybody's happy, right? Like I said in math, it's used a lot in math. So here's an example. Y plus 6 equals 9 if and only if y equals 3. There's only one solution to the first equation. And what I did was I used the definition here using this to show what they're talking about when I use the if and only if. So I could say if y plus 6 equals 9, then y equals 3, and if y equals 3, then y plus 6 equals 9. So these are the two conditional statements connected with the and you can see that this is the same as saying that. There's no other value y that I can put in here and make it 9. And there's no other, well, there are other equations, but so the bottom line is you can have a truth table for a biconditional statement. They're mostly used for math, and I'm not going to put it on the test, okay, because it gets a little confusing. And if you look at the book, the examples they give in the book I don't like because they don't make a whole lot of sense. You can create truth tables and do it, and you can do it. You can get an answer, but to me it doesn't make a whole lot of logical sense. Whereas I think it does make a whole lot of sense here when you use this example or use this example. So we're going to skip that because it doesn't make a whole lot of sense to me. Okay, the last two things in this section are there's two kinds of statements. There are consistent statements, and consistent statements, there's two statements that can be true about the same object. And contrary statements are two statements that cannot be true about the same object. So again, using an example is the best way of explaining this. So these are two statements. They're not conditional statements. They're not this is just in that section. It's just something they need to talk about. So that animal has 4 legs, so that's one statement. That same animal is a cat. So the question is, can those two statements be true about the same object? Well, in this case, the object is the animal. So can an animal have 4 legs and that same animal be a cat? Yes. So those are consistent statements. So we would, and that's what you have in the homework. You have to say whether they're consistent or contrary. So can this be true as well as that being true? Yes. Okay. You can watch the video later if you, yeah. Okay, so that here's two statements that are not consistent. I am alive. I am dead. Okay. Can I be both alive and dead at the same time? No. My last name is Nicholson. My last name is not Nicholson. Okay, I can't. That's anytime you have something and the negation of something, those cannot be consistent. So that's how you answer the question. Can the two statements be true at the same time? So this is an example of where if they're not consistent, then they're contrary. I'm trying to think of another example of a contrary thing. I am a millipede. I normally, because I could imagine somebody pulling the legs off a millipede, I normally have 2 legs. Okay. Okay, millipede has a lot of legs. Uh, so this would be two statements that are contrary, because I can't be a millipede and have two legs normally. If I pulled off all the legs except for two, yes, okay, that's true. But that's why I put the normally part in there. So here's another one. This number is a whole number. The same number is a negative number. So there, is that consistent or contrary? Can you be a whole number and also be a negative number? Well, whole numbers are always positive or zero, and negative numbers are negative. So in this case, they are contrary, because you can't be both a integer, you can't be a whole number, which is a positive integer, and be a negative integer or a negative number. Okay, so this is another example of contrary. If I said this number is a whole number and this number is even, yeah, those would be consistent, because you can be a whole number and be an even number. 2, 4, 6, 8, those are things. So, and that's it. So I'm gonna there's the homework for section 4. Those will be due next. Actually, the test. The test is next Thursday. It'll be on sections 2.2, 2.3, 2.4, 2.3. Let me write this down. I can't keep saying too many things here. So the test is 2.3, 2.4, 3.1, 3.2, and 3.3. So there will be nothing on the test about what we talked about today. But there will be things about constructing truth tables, being able to do and, or, and if-then statements, and things involving negations. There is a review video. There's also another review video about truth tables. Pardon me? Pardon me? Yes. Yeah. Yeah. In this class, if you watch the review video, the things that I cover are things on the test. So yes, if it's not on the review video, if I don't talk about it on the review video, it's not going to be on the test. I don't like surprises. You always, if somebody says just study for the test, especially in math. I mean, in biology maybe it's different, but in math, you could. I mean, theoretically, you could study everything, but there's always sometimes you study one thing more than the other because you think it's more important, and then you choose the wrong one, and then you're out of luck. So. Okay, so let's save that. Okay, so now we're going to finally get into the main reason for all this stuff. Even though, actually, we're not really going to get into it until section 6, but we're going to go through section 5 here anyway. Because it's leading up to what we're doing in section 6. We're analyzing arguments. And we want to determine whether an argument is valid or invalid. Again, this is something you supposedly covered in geometry because I looked at the SOLs again. But it's one of the first things you talk about in geometry, so you've probably forgotten it already. So there's two ways to analyze arguments. There's some special cases which we're going to do in section 5, which is looking at Euler diagrams. It's a visual way of analyzing an argument. It's only good for specific arguments that involve the words all or some. So like all students who study hard, if yeah, something like all students who study hard will get an A. Okay, that's kind of like the argument. In section 6, we would look more at if you study hard, then you will get an A. So let me explain and just use some recent examples of arguments that are invalid. So if you watch TV, you'll start to see these political advertisements. And the one that's come up recently I've seen is this one about MS-13, which is a Hispanic gang, which I guess some of the members are probably illegal immigrants. So the commercial goes something like this: MS-13, their saying is, what is it? Control, rape, and something else. I mean, it's making it as dramatic as possible. Okay, so you have MS-13, which has illegal immigrants in it. Then you have you have this whole concept of sanctuary cities, which people don't understand what that means, but they think it means that it's like in the Middle Age times, that if you were like you've done something wrong, you can go to a church and they're supposed to give you sanctuary. So you do something bad, and then you go to the church, and they're not going to turn you over to the authorities. You might, or like say when they used to persecute Jews. Sometimes, to get safe, they would go to a church, which seems ironic, but they would go to a church to protect themselves from these mobs of people, and that would be a sanctuary, and then hopefully they would either calm the mob down or they'd get them out of there. Just that's what people think of sanctuary cities. You do something bad and you're not going to get in trouble for it, which is not the case. Okay, I got to plug my computer in here. So what the commercial says is that Ralph Northam cast the deciding vote for approving sanctuary cities. Hence, because sanctuary cities protect illegal immigrants, then don't vote for Ralph Northam because he's making you get attacked by MS-13 gangs or something like that. That's the basis. That's what they want you to think. Bad guy. The reality is that the reality is sanctuary cities basically say if they pick you up for a crime that doesn't involve immigration offenses, they're not going to report you to the feds, the immigration guys. They're just going to put you in jail. They're going to prosecute you for the crime, and if you're guilty, then you'll go to prison. If you're not guilty, you won't go to prison. Theoretically, somebody who may be guilty and they don't get convicted and they get set loose, and then they could do something bad. Okay, but that's the case with everybody as far as criminals are concerned. So it's a sanctuary city so it's not what they want you to think it is. They want to mislead you. Okay, so then you have and then the other thing, the other sneaky part is that the way it worked was, let me show you how, I don't know exact numbers, but normally you have 31 Republicans and you have 29 Democrats, something like that. Okay, so it's really close as far as the Senate is concerned. So if you had one of these Republicans vote for so you took one of these guys, what would happen is if one of these Republicans said, I'm going to vote Democratic this time, you'd have 30 Republicans and 30 Democrats. And then that goes to the lieutenant governor who votes to break the tie. So there's a Ralph, okay? Now normally they would vote for it, the Republicans would vote against sanctuary cities, and the Democrats would vote for sanctuary cities, and Ralph would never get involved. What happened was one of the Republicans, the head, whatever you call it, the speaker or their head of the Republicans voted, so it would be 30-30, so Ralph would have to vote, so he votes with the Democrats because he's a Democrat, okay? So these guys did something specifically to make this happen. If they had voted traditionally, then the bill would have not passed. Ralph would not have been involved in the whole thing. So they purposely did that to make him look bad, to make him cast a vote. Which side are you going to go on? Well, if they just asked him, well, we voted it down, but we said to Ralph, hey, which way would you vote? They can't make a commercial out of that. So they did that explicitly to make a commercial that misled people. Okay, so that to me is not very nice. I mean, it happens all the time, but it's not very. That's why they do it, and I'm sure the other guys do it too. But I think the Republicans do it more than Democrats do, and make misleading ads. So then the other guy has to make an ad saying this is not true. It just seems. Yeah, so the conclusion. So back to arguments. Basically, the arguments. If you are in MS-13, then you are an illegal immigrant. And Ralph Northam voted to break the tie, but ultimately it was a tie, and so. And then you have the other branch of government which voted it down anyway, so it didn't pass. There are no sanctuary cities. And also nobody asked to be a sanctuary city. It was kind of like, if you want to be a sanctuary city, then you have the law. So it's just a completely invalid argument that they're using on the TV, but they're just trying to scare people. It's just disgusting. Okay. And whoever does it, it's disgusting. But this one is just way beyond. It's way beyond it. Okay. So what we're doing was getting back to this reasonings thing. We're going to use deductive reasoning, and we're going to make some general statements about something, and then we're going to make some conclusions. And we want to know whether that argument is valid. It may or may not be true. It may be true. The argument may be true, but it may not be a valid argument. So when we have a valid argument, this happens. An argument is valid if the fact that all the premises are true forces the conclusion to be true. So it's back to my thing about if you study hard, then you will get an A. So the way the argument would be is, if you study hard, then you will get an A. That's the first premise, which is, we're going to talk about premises in a second. The second premise is going to be, I studied hard, and the conclusion is, I got an A. Okay? So is that a valid argument? Turns out it is a valid argument. We can show that by using truth tables. And that's because if all the premises are true, so if the if-then statement is true and the statement I studied hard is true, then the conclusion should be true if it's a valid argument. If it doesn't, if it's not a valid argument, then we call it invalid. And we have a special name for that, which is called a fallacy. So an argument is either going to be valid or invalid, and if it's invalid, we call that argument a fallacy. So that's the commercial. Most political commercials are invalid arguments, or they're fallacies. Okay. There may be some truth to them, but there's, anyway, so. Oh, here's my other political. So you might have seen this on the internet, but I saw it on Fox News. So the guy so there was the congressional shooting where the guy was practicing baseball and this guy came and shot him. So the guy who shot him was 62 years old, I think. He was an older gentleman, older than me slightly. So you have an older guy, he's a Bernie Sanders supporter, and he shot a Republican senator. Okay. So this liberal guy shot this conservative guy. All liberals are, crazy. So what happened was, with the shooting in Las Vegas, this guy came on and said, well, if you look at the demographics, this guy is 64 years old. He's an older white guy, and he shot at a country music festival. And most people who go to country music shows are Republicans, and they supported Donald Trump. Therefore, this guy shot these people because he doesn't like Donald Trump. And he's some liberal guy, okay? So that was another argument. if you are 62 years old and Bernie supporters saying, then you shoot people. So if this guy shot people, he must be a liberal. It's so that's crazy. But a lot of people take that. They think, oh, this guy's an expert, so we're going to believe him. Okay, so one means of checking validity is using Euler diagrams. And basically, they consist of making a couple of circles and a little x. And we use the argument to draw the circles or to identify the circles. And we use the conclusion, the second part of the argument, to draw the little x. So I'm just going to show you an example of how it works. So here's the logical argument, and we're trying to figure out whether it's valid or invalid. So it consists of two premises. One premise is all disc jockeys play music. Notice the word all. So you typically have to have something like all to be able to use Euler diagrams. The second premise is this guy named Flash Phelps is a disc jockey. Besides his name sounding like a disc jockey name, Flash Phelps is a disc jockey. So those are my two premises. My conclusion is that Flash Phelps plays music. Again, this may be a true statement, but it may not be valid, or it may be a true statement and it is a valid argument. So the way that we do this is the word all is associated with disc jockeys. So the part of the argument that uses all is the inner circle. So I'm going to identify the inside circle as disc jockeys. And the second part of the premise play music. The big circle is people who play music. So by saying all disc jockeys, that means that this circle has to be inside the bigger circle of people who play music. So I was able to identify both circles by this sentence. Then the next sentence, which is the second premise, Flash Phelps is a disc jockey. So here's Flash Phelps. We'll put him in the circle for disc jockeys. So this makes it so I have to put him in the small circle. By doing that, he's also, as a consequence, in the big circle. So the big circle is people who play music. So if this is Flash Phelps, PP, and he's a disc jockey, and all disc jockeys play music, then he must play music. Okay, so this, because this little x is inside the small circle, which is inside the big circle, this is a valid argument. So we're doing it graphically. It's valid if the x, which comes from here, is inside the small circle that's inside the big circle. Okay, let's do an example where that doesn't happen, which is an invalid argument. It may be true, but it may not be a valid argument. So all politicians, just like all disc jockeys, so I'm going to make the inside circle politicians. Politicians are a subset of people who lie, so we'll say people who lie, cheat, and steal. I didn't make this as one out of the book. I'm trying to be too political here. Okay, so all politicians lie, cheat, and steal. Then we use the second one, that man lies, cheats, and steals. Well, this statement doesn't allow me to put him in the middle. He may be here, but we don't know. Because if I put him here, yeah, he's in the big circle, but this doesn't force him into the small circle. So I can only put him in the big circle, not necessarily in the small circle, because of this statement. So that means this man is a politician. That doesn't force, the second one doesn't force him into the smaller circle. So because I'm positioned here instead of here, then it's an invalid argument. Now, if I switch the order here, if I put this here and that there, then it turns out it will be a valid argument. So let's just show you how that works. So I'm going to have the same three sentences. I'm just going to switch the conclusion with the premise. All politicians lie, cheat, and steal. The second one is that man is a politician. And the conclusion is that man lies, cheats, and steals. So what I would do to make this, to do the Euler diagram to represent this, is I would have a big circle like that. So I draw a big circle. You always draw a big circle, a smaller circle inside the big circle. Again, the first sentence allows me to identify the two circles. Politicians, all politicians, people who lie, cheat, and steal. Okay, that man is a politician. Well, that means he has to be inside the small circle because he's a politician. As a consequence, because he's in the small circle, he has to be in the big circle. So this is a valid argument. Okay, so let's look at one, see if you can, well, that's the same, basically the same thing. So I said he is a politician instead of Bill is a politician. So this is the example of the valid argument. And as I said before, arguments can be true but still invalid. So I go back to this one, which is an invalid argument. And all politicians lie, cheat, and steal. That man is a politician. Therefore, that man lies, cheats, and steals. That's the valid one. Where's the invalid one? All politicians lie, cheat, and steal. That could be true. That man lies, cheats, and steals. That could be true. And that man could be a politician. It's because he could be here or he could be there. We don't know. So your homework is basically taking logical arguments like this and taking the first sentence, making sure that the all, whoever you identify as the all, goes in the small circle, and the big circle is the second part of the sentence. And then use the second sentence to see if you can force it into the smaller circle. If it has to go in the smaller circle, then it's a valid argument. If it doesn't force it into the small circle, then it's an invalid argument. So let's do one more example, and then we'll move on to the next section, which we'll spend more time on. So here's the argument. All chickens have beaks. That's true. All birds have beaks. That's true. Therefore, all chickens are birds. Okay, that seems like a valid argument because everything is true. But all chickens have beaks. So here's chickens. Here's things that have beaks. The second one, all birds have beaks. So here are birds. And that's, again, you can't use your knowledge of birds and chickens and things like that. You can only base this upon the words in the argument. So because the only way I could make birds surround chickens is if I said that a bird is, up here I'd have to say that chickens are birds. Okay, then I would know all chickens are birds. Then I could put this circle around it, but just saying all birds have beaks, all I can do is put this circle inside the big circle. I can't assume that that's the case based on I have to assume I know nothing about chickens or birds just based on the words. So when you say all chickens are birds, then you can see that the only way that could happen is if this big circle was in this circle. So how would I rewrite that so that it would be a valid argument? So I would say, actually, it would have to be all chickens have beaks. All chickens are birds. So what does that do for me? Here's my chicken. Then all chickens are birds. So then I would put. Let's draw a picture here. So let's construct our picture here. So here's my things that have beaks, and then I'm going to have another circle, which is the first one. So based on my first sentence, I would have things that have beaks. And this is chickens. Okay, chickens. All chickens are birds. I'd also need to have that all birds have beaks to make it work out. Because even in this case, it's not quite as easy as it seems, because I could have a circle like this. So all chickens are birds. I don't know that, again, I don't know that birds have to have beaks, or things that have beaks. I'd have to have an additional statement that would say all, whoops. So all birds have beaks. Okay, what that would do is it'd be allow me to take this one and shrink it down and stick it inside the, I'm trying to get it, so there we go. I gotta make it smaller so it fits inside. Shrink it down about that size. Okay, there we go. So this would be birds, right? So this would agree. Things that have beaks. All chickens have beaks. All birds have beaks. Birds are chickens. Chickens are birds. Okay. And then you might have something like Bill is a chicken. And then the conclusion would be Bill could be either a bird or he could be a thing that has a beak. That could be the conclusion that would be allowed, because by putting Bill as a chicken, I put him inside here. And because he's in here, he's also in here, and he's also in there. Okay. That's a little complicated, but and we're going to skip that for right now. And I'm not going to sign this until this. Well, I'll sign it, but it's not due next Thursday. It'll be due the following Tuesday. Okay, so you have the test next Thursday. So this will be do the class after that. So what we're going to do in the next 9 minutes is we're going to go to the next section and kind of give you an introduction to what we're going to be doing. I'm going to spend a little more time on this because I do put a test question like this, and some people get it, but too many don't get it. So I'm going to try to spend a little more time so that more people get it this time. And ultimately, this is where the whole concept of truth tables and truth values has some practical use. The other practical use is that truth tables you can relate to computer science and computers, so that's also useful. But so let me save that. So this is 2017 Tuesday, Thursday. Okay, so we're going on to section 6. You're like, man, you're covering a lot of stuff today, but don't worry. It'll be okay. You'll survive. Okay, so what we're going to do is we're going to analyze arguments with truth tables instead. This has more general applicability. So back to what is an argument. We kind of alluded to it in the previous section, but it consists of two or more premises. The premises can be just statements. They can be compound statements with ands or ors. They can be statements with if-then type things. Usually there's an if-then, and then there's a statement. And then you draw a line, and then the conclusion is underneath the line. So you've got premises and then a conclusion. And what we're trying to do is figure out whether the argument that we present is valid. The premise consists of statements, so we're going to convert those statements into symbolic logic. The conclusion is going to be a statement. We're going to convert that to symbolic logic. And then we're going to make a big, long combined statement that connects the premises to the conclusion using the appropriate logic arguments, like and or if then. And then we analyze the table and we look at the last column that we end up with, and if it turns out if those are all true, then the argument is valid. Otherwise, the argument, anytime you get any falses in that last column, it's an invalid argument. Again, it may be true, the argument may be true, but it's not a valid argument under all circumstances. So the rules where you're going to, the premises, so we're going to have two logic statements here for the premises. We're going to link them with an and statement. So we're going to say, for example, if you study hard, then you will get an A. That's the first premise. And he studied hard. That's the second. He studied hard is the second premise. I connect those with the and statement. Then you say, then, then you have the conclusion. The conclusion would be he gets an A, which is also a statement. You'll connect the premise, these premises in the conclusion by a if-then, the conditional statement. Again, it may not say if-then. It may say therefore, something like that. So again, I'll use that example. If he studies hard, then he will get an A. That's the first premise. He studies hard. That's the second premise. Therefore, he will get an A. So I'm not using the word if-then, but I'm going to use the rules for the if-then statement in constructing the entire logic argument. So we can say premise 1 and premise 2 implies the conclusion. Implies, we used that word earlier to show that's the same as an if-then statement. But we may not say it directly. So let's just look at an example, show you how you put this all together. We won't get to the end of it today. So this is an example in your book. It's one of the homework problems. So we start with an if-then statement. This is premise 1. Okay. If Julie Nem works hard, then she will get a promotion. Again, the then's not there, but it's implied. So let's call this premise 1. Okay. Premise 2 is, let's say she works hard enough. Whatever, hard, it's hard to define what hard is. That's how do you feel today? Fine. That's not a very good descriptor, but so. And then you have the conclusion, which is Julie gets a promotion. Okay. So what we do first is we take the individual premises and we create a symbolic logic statement. So we have to identify what the letters represent. So the letter P represents Julie Nem works hard. Just like we've been doing this earlier. Q is the statement, she will get a promotion. So there's only two statements. This involves statement A, this involves statement B, this involves statement A and B. So the first premise, if we convert that to symbolic logic is we have if P then Q. So we write P arrow Q, which is if P then Q. So that's the symbolic logic for the first premise. The second premise, Julie Nem works hard. I left off enough here. She works hard. Okay, works hard. I forgot to write that in there. She works hard. So by our definition of what the statements are, that's just statement P. So the second premise is P by itself. The conclusion is statement Q, basically. She gets a promotion. Julie gets a promotion. So we identify the conclusion as Q, just the statement Q. So we've got the first premise, if P then Q, the second premise P, the conclusion Q. So what logic statement do we use to analyze the validity of this argument? So what we do is we take the first premise, if P then Q, we connect that to the second premise with an AND statement. So we'll put this in parentheses. Put the AND statement, and P, so that's the second premise. And then we connect the results of the premise with the conclusion using an if-then statement. Again, even though we may not say, if I tried to make this if, you'd use if twice. If Jen Nem works hard and she will get a promotion, and Julie Nem works hard, then Julie gets a promotion. So it's not always written out exactly like an if-then statement, but we always use the truth table rules for the if-then statement when we're connecting the premise with the conclusions. So here is a logic statement that we should be able to do based on what we've done before. We'll fill out the truth table for this logic statement, and the final answer will be in this column. The final answer for our logical arguments is always this if-then statement that connects the premises with the conclusion. When we look at the result of this column, if they're all true, then it's a valid argument. If any one of any one of the entries in that column is false, then it's not valid or it's invalid. So what we'll do next time is we'll create a truth table for this logic argument and see what we get and prove. It seems like a logical argument, doesn't it? I mean, it seems like if I tell you this is going to happen and this first thing happens, then the second thing should happen. So it appears to be a valid argument. And it is a valid argument. We're going to show how you prove that using truth tables. Okay, so that's it for today. See you on Tuesday.